Hey everybody. So we're going to move forward from our last videos into something called the fundamental theorem of calculus. And I'll do it in two parts, so there'll be a couple of videos about this and probably a couple more following up. So we're going to start by looking at a particular way to define a function. So I've got here a graph of a piecewise function. Let's just give this thing a name. So let's call this function that's graphed here f of x, okay? And what I'm going to do is define a function that I'll call g of x as the following. I'm going to call it 0 to x f of t dt, okay? Now, this is a pretty interesting way to define a function. Let's think about what this thing means. So for instance, g of 0 just means plug 0 in for x, which is the same as saying integrate the function f from 0 to 0. In other words, there is no, we're finding the area between 0 and 0, which there isn't one. This is one of the properties of definite integrals, that if you integrate over a single value like this, you get 0. Okay, let's make it a little more interesting. G of 1 gives me the integral from 0 to 1 of f of t dt. Right now, look what we've got here. We're saying integrate this function f from 0 to 1. Wherever I see an x, right, g of x equals the integral from 0 to x. I put in that number for x, and then I'd have to compute that integral to get this number. Okay, now my scales are a little off here, but this piece of the function is a quarter of a circle. It's skewed because the scales aren't precisely right. And so the area from 0 to 1 that we're talking about has an area of, it's a circle with radius 1, so its total area is pi times 1 squared, or pi, since I'm looking at a quarter of it, that would be pi over 4. So what does this function do? This function spits out the value of the area from 0 to whatever x value I put in between this function f and the x-axis, right? In a picture, right, the value of g is the area I see here. So at g of 1, we see pi over 4, right? That's what that area is, that quarter of a circle. Notice that as I continue going forward, right, for instance, this right now, what I'm showing on the screen, the shaded area, this would be g of 3. It's the integral from 0 to 3 of f. I've got the computer computing this for me. We can see g of I called it k, so whatever my input is k, and that was negative 2.356, let's say, rounded. Notice what happened. We started out with this pi over 4 area, about 0.7 something, and then we started getting negative areas, right? And so we are, in this case, the area is the negative area is more than the positive area, and so we end up with an overall negative area, right? And if I continue putting in values for k, for x, we're getting more and more, we're moving further along this graph. This is where it ends, and that would be the integral from 0 to 6, right? So this would be g of 6, the area represented here, where the blue part's negative and the orange part is positive. Okay, so this is a function. It makes sense. You put in a number, right? So functions are always a set of instructions. If I give you the function something like, you know, h of x equals x squared plus 1, it means if I give you a number, square it and add 1 to it. That's the set of instructions. This is a more complicated set of instructions. I say g of 3. I say given the number 3, integrate the function f of x from 0 to the number you put in, and report back the area. That's the set of instructions, and so you have to go through this whole process. Okay, so that's our first idea. Okay, but let's look at something here. Something interesting shows up here. G is a function right? I've just put in the value 1, output the value 0.4. This means the point 1 comma pi over 4. Let's get a decimal approximation for that. So if I go back to 1, the decimal approximation is 0.78. So 0.78. That should be a point on the graph of G. If I look at this, the next line, I see that the 0.3 comma negative 2.356 should also be on the graph of G, right? So if I let's put these in. 1.78 is approximately here. 3, negative 2.3. Let's see, eyeballing it, maybe down here somewhere. There's 2 points on the graph of G. Well, I let the computer input a bunch of points and output a bunch of values and put those points together to look at a graph of this function G. My points are a little bit off, but I was fairly close. So this green line is the graph of G, okay? So I'm gonna erase this other stuff now and just look at the graph of G, right? So the values of G, let's leave 1 up for a moment. The values of G, for instance, at G of 1, here's the value of G. This is that 1 pi over 4. The input values tell you how far along you're integrating in this definition of G, and the output tells you what's the area up to that point, right? So at each point along this graph, the y coordinate tells you the area under the red graph up to that point. Okay, so there's a little bit of, it's a little bit confusing, but it should make some kind of sense here. We're just spitting out areas. So let's just look at this function alone. There's a relationship between f and g besides the one I've defined here. So let's notice something. So if I change, let's go back to this. As I'm increasing my x value, I'm integrating over more and more of this function, more and more of its domain, right? Look at what happens as I pass through 1. On the left side of 1, I'm adding all this positive area. As I increase x, I'm adding all this positive area. And as I go past 1, I start adding negative area. So look at our values of g. To the left of the value 1, it's rising because we're increasing area. But then as we hit 1, we start adding negative areas. So the value of g starts getting lower and lower and lower. And it continues to travel downward, right? It's still traveling downward until we hit the value 4. Because after the value 4, the areas start to increase. And so now we've gotten all this negative area, but see this green curve starts to curve up. It's getting more and more positive area now. And until it keeps continuing to grow as we add more and more positive area. Okay. Notice what's happening here. For instance, at x equals 1, the tangent line of g is 0. Right? That's its peak. It's increasing area to the left of it, decreasing area, negative area to the right of it. So that's its peak. Same thing over at x equals 4, right? It's decreasing on the left of 4, increasing on the right of 4. And f, the value of f at those points is 0. We've seen this relationship before, right? When you study derivatives, if you have a function wherever its tangent line is equal to 0, that's where its derivative is equal to 0. In other words, at g prime of 1 equals 0, we can also see that f of 1 equals 0, and g prime of 4 equals 0, and f of 4 equals 0. So one thing we might ask ourselves is, are these the same function? I found 2 places where they're equal, right? It's not huge evidence, but I'm curious. I also notice that where the tangent lines of G would be positive. For instance, between 0 and 1, you can imagine drawing a tangent line on this graph. Notice the values of f are positive. Notice as the tangent line seems to get more steep, right? This appears to be some of the steepest part of the graph, is also where we have the most extremely negative values of f. And same thing over here, this appears to be the steepest part of the graph of G, and it's also where f has the highest values, right? Those are the same correspondences we get between a function and its derivative. So what I'm curious about now is the derivative of G equal to f, right? That's a question, okay? So I'm going to, you're probably already guessing it's true. It would be a little strange to bring it up only to say, turns out it's not, moving on. This is true, and I'm not gonna prove it, but I am gonna give you a little intuition, I hope, as to why it's true, more than just this picture here. So let's go to a blank page and generalize this just a little bit, okay? So let's say, oops, sorry, I need to turn those off. I believe I'm still sharing this. Oh, I'm still sharing this. We'll see at the end. All right, so let's draw an arbitrary function. Let's make it red maybe. So here's some function, okay? And let's say this function is continuous from A to B. Again, I'm only drawing the x-axis, not the y-axis. It's only going to complicate this function. Let's give this function a name. I'm going to call it f. And let's do what we did before and define a function g of x is equal to the integral from a to x of f of t dt, okay? Now, x is our variable here. T we often call like a dummy variable. We're just using it to stand in for the input, and we don't want to call them the input x's. If this is my x-axis, they're all x inputs, but the t over here isn't really a variable. We're just saying integrate across this whole function with respect to the input when you compute the area, okay? All right, so let's look at a couple of little things. If I took, with this function in mind, if I took g of x plus h minus g of x, okay? What does this represent? Well, we're looking at let's start with g of x plus h. Actually, let's start with g of x. G of x picks a value between a and b. I should say that x is going to be between a and b for this to make sense. We're just looking at that interval. And g of x would spit out the area between a and x. Okay? Let's put in x plus h. G of x plus h would spit out the area from A all the way out to x plus h, right? I'm drawing this as if h is positive. It's a reasonable assumption at this point just to help us understand this, okay? Now, if I take these two things and subtract them, so I'm taking the area represented by the green shaded area and subtracting the area represented by the blue shaded area, what do I get? Well, all I get is this little strip between x and x plus h. So let me erase some things. Hopefully I can get just the pieces I want. Let's put a new color in here. I'm just going to get the area between these two graphs. Let's just make it blue. All right. I'm going to get this. Well, what is that area? Well, we could approximate this area pretty easily with our approximating rectangles. So I can draw a little rectangle in here. Right? I've chosen a left endpoint here. It doesn't really matter, though it makes the next step more obvious. What's the area of this rectangle? Well, what's the width of this rectangle? I just take the difference between these two x values, x plus h minus x, gives me a width of h. And I multiply that by the height. What's the height? Well, this point right here is x f of x. That's the height. Okay. So these two things are approximately equal, right? This is my approximating rectangle. If h is small enough, these are going to be very close, right? You can imagine as I get closer in here, this approximation gets better. Let's divide both sides by h. Right. What we see on the left should be pretty familiar. Let me draw this a little more neatly. Right. That is the difference quotient for the derivative of g. Okay. And so what we say, right, I'm not really proving this. This takes some work to prove. Proofs of this are out there if you're very curious, but I just want our intuition to be there. As we take the limit as h goes to 0, as this rectangle gets closer and closer together, right, as I move it in and I'm looking at this rectangle, the difference between the value of f of x and this g of x plus h minus g of x over h becomes less and less because this approximation becomes better and better. And so in the limit, they become equal, right? And this left-hand side is g prime of x. And so when we make this definition, we define g in this way, its derivative is what we call the integrand over here, the function f, okay? This is a pretty amazing connection, right? That this connection between, we were talking about area and suddenly it gets looped into the idea of the derivative, right? We'll talk more about this connection as we go forward. We saw a little bit of a hint of this when we looked at velocities and distances. I'll make a different video to explore that idea a little more. I'll let this kind of stew with you for a little bit. Let's, though, present this. Have it typed up here. If I know how to use this thing, I might be able, there we go. That's how you grab things. There's a fuller statement of this fundamental theorem of calculus part 1. If f is continuous on AB, and hold on, I'm going to see if I can figure out how to make this bigger. Pardon me, I'm still new to this program. Ah, that's better. Now let's make it bold too. Okay, that looks better. If f is continuous on AB, the closed interval AB, and the function g defined by g of x equals the integral from a to x f of t dt, where x is between a and b inclusive. So then g, we know, will be continuous on the closed interval AB and differentiable on the open interval AB, and its derivative is the derivative of g prime of x is equal to f of x. Okay, so as long as f is continuous, then this g is going to be continuous on the interval and differentiable on the interior of the interval, everywhere but the endpoints. Okay, there's also some notation up here, sometimes called Leibniz notation. Maybe I'll write it a little bit nicer because the typesetting doesn't look great there. That we can write this relationship as, I'll do it here, d dx. If you take the derivative of an integral defined this way, you get f of x, right? The integral from a to x, f of t dt, its derivative with respect to x is just f of x, okay? Now, let's give a little more intuition to this thing before we move forward just a little bit. This is what we were hinting at here. The way I've always thought about this is g is a function that is spitting out areas, the area under the curve from a to x, right? A derivative measures how much something changes by, right? Well, as we slide x forward, right, I've always imagined what we're doing, right? So if I take the area from A up to some value x, right, I get all this area. As I slide x forward, right, the change is like, I just imagine little strips being added to this area, right? If I move x from here, if I take a higher value of x, and how did our area change? It's by how high f is. The higher f is, the more area we're grabbing. If f is smaller, the less area we're grabbing. F kind of tells us how fast we're changing our area, right? Or another way to think about it is, if the function were constant at this point, right? If the function just had a horizontal line here, a change in x, a unit change in x, would give us a rectangle of that height times 1. And that's really what a derivative measures. If we kept changing how we were changing at this moment, what would it look like? And that would mean we get the same amount of area in each step forward, right? We know that it changes though because f is increasing, but we just look at this is the idea of this instantaneous rate of change. If our rate of change wasn't changing, what would it look like? And that's what this thing tells us. Okay, last thing with this for this video, I just want to make perfectly clear, well, two little things. Perfectly clear how we're mostly going to use this for what comes next, the second part of the fundamental theorem, which is something we use a bunch. This one is useful, and it is useful down the road on its own, but we use it mostly in this set of videos just to do what's coming next, which we'll be using quite often. But we do want to understand how this thing works, and it's just as simple as it says it is. For instance, if I told you that g of x was equal to the integral from 2 to x of cosine of e to the t dt, right? Well, cosine is continuous everywhere. E to the t is continuous everywhere. The composition of continuous functions will be continuous on their domains. And so we get, we satisfy the conditions of this. The domain of this, of both of them, is infinite. So our a and our b are you know, we can choose any interval here, 2 to whatever we want. If I ask you to take the derivative of this, all we do, exactly what it says here, we're just copying this function, except we're using x now. The derivative of g is cosine of e to the x, right? The integrand, the thing in the integral. If I give you some horrible, complicated function, like the natural log of the sine, let's make it squared of x plus 1 all over 7. Oops, this should be t. Pardon me. dt, right? We're okay here. We know that sine squared is always going to be 0 or positive. So plus 1 means this is always defined. Dividing this is fine by 7. So when I take the derivative, even though it looks like a very complicated problem, I'm just putting in sine squared of x plus 1 all over 7. Okay, so we don't have to look at this thing and take some kind of chain rule here, because this isn't really the function. The function has to do with the integral, right? It's the instructions are to take the integral and spit out the area. However, let's complicate things just a little bit. Let's do one more of these. Let's say I give you the function h of x equals, let's go with -2 sine of x t squared e to the t dt. Okay, so now Let's think about what this function is telling us to do. It is saying, if I input a number x, take the sign of that number, put that number as the upper bound of an integral, and then integrate from -2 to that number the function t squared e to the t dt. It's a complicated set of instructions, right? The most complicated part is the part that says take this integral, right? Because that means setting up an infinite sum, taking the limit as it goes to infinity and all that stuff. So it's a complicated function, right? Taking the derivative of it isn't actually all that bad. Let's see what we can do. I'm going to start by saying g of x is almost the same thing, except I'm going to skip putting the sign in here. Right? And we know from the fundamental theorem of calculus part 1 that g prime of x is equal to x squared e to the x dx. Right? That's what we just did. Not dx, the x squared e to the x. Let's do this. G of sine of x. Okay. Which is going to be -2 sine of x t squared e to the t dt. Well, I know how to take this derivative. The derivative, this is a composition. I use a chain rule. So if I were to take the derivative, g of sine of x, using the chain rule, I get g prime sine of x times the derivative of sine, which is cosine of x. Okay. Well, I already know g prime. I just did g prime right up here. So this is g prime of, instead of x, of sine of x. So what I'm going to get is sine of x squared e to the sine of x, all of this times the cosine of x. Okay. But notice one more thing. G of sine of x is equal to h of x. All right, look at what I wrote right here. This expression on the right that I've got the star by is exactly the definition of h. And so the derivative of h is just the derivative of g of sine of x. So all of this is to say h prime of x is equal to sine of x squared e to the sine of x cosine of x. So we do get a little bit of complication when we do something like this, where we put a function in the integrand, but it's not unmanageable to deal with. Okay, I want to end it there. We'll come back with the second part of the fundamental theorem, which is really the part we're going to focus on a bunch for quite a while now. Okay, I'll see you on the next one. Thanks, everybody.